Hello and welcome to the Team 2 final project. Our project is called the Sync-in Social AI Support Agent, and our team members are Pros Luong, myself, Thomas Derossi, and Raj Chandarana. Team Contribution Map. This slide shows how our team divided the project across three main roles. My role focused on production, context, and dataset foundation. I helped frame the sync-in social support problem, define the types of questions the agent needed to answer, and build the structure around the 43 support and policy documents. 243 synthetic support questions, expected answers, expected KB document IDs, escalation labels, and human review criteria. Pros owned the data engineering side. That included building the Spark data frames and Delta tables, running quality checks, validating the dataset, chunking the knowledge base into 72 retrievable chunks, generating embeddings, and preparing the vector search layer. Niraj owned the AI engineering section. That included the RAG workflow, LLM prompt answer generation, ML flow, traces, two model comparison, graceful rejection examples, and demo workflows. Together, these three sections connect the full life cycle: product need, data pipeline, agent design, evaluation, and business value. Business problem that we focused on is that sync and social users can ask a lot of repeated support and policy questions. These might involve profile setup, rejected content, pro-verified features, business ad credits, privacy rules, notifications, or troubleshooting issues. A generic LLM could answer some of these questions, but it could also hallucinate policies or give advice that does not match up to the actual app. That is why we designed the agent to retrieve from Sync-in social specific policy documents before answering the questions. The support goal was to make responses fast, grounded, and safe. The workflow is simple. The users ask questions, the agent checks whether it is in the scope, retrieves relevant sync-in policy, grounds the answer in the retrieved context, and generates a response. And then it will escalate when needed. Escalation is important because some issues should not be guessed by an AI system. If a question is account specific, billing related, safety related, legal, or unresolved after troubleshooting, the agent routes to the user the syncinsocialsupport.com email address. If there is an immediate danger, the agent should direct the user to an emergency service first. So the main value here is that the agent reduces repeated support work while still protecting users and keeping answers aligned with the actual project. For the dataset, we did not rely on a public dataset because Sync and Social needed platform-specific answers. Instead, we created a custom support database built around actual types of questions a user might ask inside the app. The knowledge base included 43 support and policy documents. From those documents, the data pipeline created 72 retrieval chunks that could be embedded and searched. We also created 243 synthetic support questions, which became the evaluation set for testing the agent. Each evaluation row included more than just a question. It also included the expected answer, expected KB document IDs, scenario type, difficulty, escalation label, and data split. That made it possible to evaluate not only whether the agent answered, but whether it retrieved the right policy, stayed grounded, and escalated correctly. The human evaluation process was also important. As a team, we reviewed sample outputs and asked five main questions. Was the answer correct? Was it grounded in retrieved sync and social policy? Did it escalate when needed? Did it safely reject private data or unrelated requests? And was the final answer clear enough for a real app user? This helped us improve the agent from a class prototype into something much closer to a production-ready support assistant. After hardening the retrieval logic, escalation rules, keyword coverage, guardrails, the final evaluation improved significantly, especially on retrieval and escalation accuracy. That completes my section. From here, Pros will explain how Data Pipeline prepared the knowledge base, chunks, embeddings, and vector search layer that made the agent possible.
Hi, I am Pros, working on the project data pipeline. The data pipeline built a foundation for RAG agent in Notebook 2 by creating and validating 43 knowledge base document and 243 synthetic support questions, then writing them to Delta table. It chunked each document into finite character passage with 50 character overlap, convert chunk into 1024 dimensional embedding vector using the Databricks embedding endpoint model, and set up vector search infrastructure. This enabled Notebook 2 agent to instantly find semantic similar knowledge-based chunk for any user question, even when phrased differently than the original documentation. Without this output, Notebook 2 cannot retrieve knowledge, generate answer, or be evaluated. For data preparation and quality check, the pipelines transform raw knowledge base and question data into production-ready Delta table through three steps. First, it defines explicit schema that specify exact column type and requirement, ensuring anyone running the notebook get identical data structure. Second, it validates data quality through six check: category count, difficulty count, scenario type coverage, escalation label distribution, split count, and missing doc ID check. Prove every question reference existing knowledge base document. Finally, it write validated data frame to Delta table with versioning, metadata, and asset guarantee, satisfying the assignment data pipeline requirement by creating reproducible, evaluation-ready dataset. For chunking and embedding, the pipelines transform 43 knowledge-based documents into 72 retrievable ready chunks, 500 character each with 50 character overlap, preserving parent metadata, doc ID, title, category. Each chunk is written to chunk table with a unique ID. Chunk preserve the policy context used by the LLM. The embedding generation process run one batch at a time to avoid overwhelming the API, calling the Databricks model endpoint through MLflow deployment agent. The resulting 72 1024 dimensional vector are written to embedding table. The embedding table is the bridge between data and the agent. Semantic matching find meaning, not just exact word. The vector search setup build a smart system that find a relevant policy by comparing question meaning to stored knowledge chunk. It automatically update when information changes and create a searchable index from 72 chunk, enabling the agent to match policy based on meaning, not just exact word. Notebook 1 produced five output: KB table, question table, knowledge chunk table, embedding table, and vector search index. Notebook 2 uses these for retrieval and answer generation, the bridge between data engineering and AI engineering. From here, Naraj will cover agent definition and evaluation, retrieval function, rack prompt, LLM call, trace, model comparison, graceful rejection, and reporting.
Hi everyone, I'm Naraj, and I'll be walking you through the AI engineering architecture for the Sync-in Social Support Agent. This slide 9 illustrates our core RAG agent workflow. When a user asks a question, the system first performs a scope check to ensure the request is valid. From there, we move into the retrieval phase, where the agent pulls relevant policy chunks. This context is passed into the RAG prompt before the LLM generates an answer, which finally passes through an escalation gate. Our core focus for the agent's behavior was ensuring it handles routine support seamlessly while safely escalating sensitive cases. It is also designed to reject unrelated or private data requests, ensuring that all responses stay strictly grounded in our approved knowledge base. Moving to the slide, let's look at our evaluation matrix and how hardening the system impacted the overall accuracy. We evaluated the agent across our full dataset of 243 rows, utilizing MLflow to log matrix and collect traces. We also performed manual rubric scoring to accurately measure correctness and grounding. After implementing robust guardrails and improving our retrieval strategy, we saw a significant jump across the board. Our retrieval hit rate improved from 73.3% to a final 96.3%. Correctness and grounding reached impressive scores of 4.79 and 4.52 out of 5, respectively. Crucially, our escalation accuracy for safely routing issues surged from a 60.1% to a near flawless 98.4%. On this slide, we cover our model comparison and the return on investment analysis. We tested two distinct models to evaluate the trade-off between speed and accuracy. Llama 3.18b proved to be highly effective for fast routine support with a latency of just 849 milliseconds. Llama 3.370b took 1762 milliseconds but serves as our accuracy first production model. Assuming a volume of 10,000 monthly support questions and a $25 value per successful automated answer, the net value is increasingly close. 9,990 for the 8B model versus 9,980 for the 70B model. Given these margins, our recommendation is to deploy the stronger 70B model where accuracy and safety are paramount while closely monitoring operational costs before scaling up. Finally, the slide covers our deployment strategy and the key takeaways. We recommend deploying this as an in-app assistant that strictly answers using the approved RAG knowledge base. It should automatically route any account billing, safety, or legal issues directly to our human support team at support@syncinsocial.com. Continuous trace logging and KB refreshes will be vital as app features change. Reflecting on the final product, the agent performed exceptionally well on routine support, moderation policies, and general troubleshooting. The primary lesson from this project is that production grade AI isn't just about the LLM. Its quality relies entirely on clean data, precise retrieval, robust guardrails, and ongoing evaluation. All of our evidence, including the two code first notebooks and README, are available in our GitHub repository.